All right, we're going to continue talking about the rates of reactions, and now we're going to discuss about how different factors affect the rate of reaction. In the first video, I talked about this imaginary container where you have particles of reactants going in random directions all over the place and bumping each other, and most of the time they bump each other, nothing is happening, and occasionally a bump is kinetically powerful enough where you can overcome the activation energy barrier to make products. And we talked about how we drew these rates of reaction onto a graph. And so what we have here is simply a graph on the axis, and we talked about how we collected those data. Here we're going to imagine that is the volumes of gas produced. So we collected in the syringe, right? And we talked about at the beginning of the reaction there are a lot of reactants. So the rate of reaction is really high. But as the number of reactants gets used up to make products, less and less reactants are available. And so the rate of reaction kind of like decreases. And eventually it will plateau out as all the reactants are used up and only products are left. So you get a curved graph in this way. And we also mentioned about how we can measure the rates of reaction by mass loss, right? So you have reactants reacting really quickly as there's lots of it available, bumping each other in all random directions. Most of the time nothing is happening. Occasionally something does happen, and then there you go, you form products. But as the reaction continues and the amount of reactants becomes less because products are being made and the products is evaporated, right? Because it's a gas, you get less reactants happening, and so the rate of reaction will decreases and eventually plateau out again as you use up all your reactants. Okay, and we in class we did the qualitative method where we look at the precipitation and just time the total time it takes for the reaction to go to completion, and we plot it over 1 over time, right? So here we have 1 over time, and this is the independent variable, the independent property, okay? And then we plot it in whatever plots we had, and we did a best fit line, right? And I talked about how a curve becomes a straight line when you do a 1 over time factor, which means you calculated that rate in that instantaneous point of time, or that property. But now we're going to talk about the effects of concentration on the rates of reaction, okay? And so we're going to talk, firstly I'm going to talk about what is happening using collision theory in terms of how rates of reaction are different when you talk about different types of particles, okay? So in this first instance, we have about 5 blue particles and about 5 orange particles. And it's a big container, and it has this limited amount of reactants in it. And so, they're bumping each other, they're going all in random directions, some slow, some fast, and some fast becomes slow when you bump into each other and stuff like that. And occasionally they will bump, if the blues bump both blues will occasionally bump the oranges, and oranges will bump themselves. And most of the time when they're bumping each other, nothing is really happening. So the rate of reaction tends to be kind of slow, right? Because there's not a lot of them available, and the chances of a lot of them bumping each other successfully, the blue and orange bumping each other successfully, it's not so high. So it's kind of slow. It's a slow start. Occasionally, the kinetic energy between the orange to the blue is good enough where when it bumps, the kinetic energy is good enough to overcome the activation energy barrier. We talked about the activation energy barrier, right? This little bump in order for the reaction to happen, right? This little bump in the energy profile for the reaction to happen. So it does overcome that activation energy barrier, and so products are made, all right? And so it will continue to slowly make those products, and then once all the orange particles binds, forms new products with the blue particles, there's no more reactants left. And so when we draw the rate of reaction in terms of the volumes of gas produced, you will ultimately just have this amount of products made. So no matter what, the amount of products you make is around this high. But the rate of reaction, because there's so little orange particles available for reacting, your rate isn't that high. So it will go like this. It will also plateau out, right? It's not a very good graph. So it's still quite high compared, but it will plateau out. So it will plateau around here, and then it will, the rate of reaction will go over there slowly, reduce, and then it finishes up there. All right, so that is like the rate of reaction for the first instance. And now we're going to talk about the rate of reaction for the second instance. Now, I've increased the concentration of the orange particles, as you can see, all right? So there's a lot more of it here. And again, they're still bumping each other and in random motion and colliding with each other. And nothing is really happening, but occasionally something does happen. And so it's moving around, some slow, some fast again, but occasionally one blue and one orange will meet up with enough kinetic energy to bump each other and form the products, all right? But because there's more orange particles available, the chances of blue hitting the orange has increased, right? So that initial rate of reaction, it is a lot more because there's a lot more orange particles available. And so when we draw the rate of reaction, the initial rate of reaction does go up. And then it will slow down as the number of blue particles are available, and then it will plateau out as soon as all the blue reactants have been used up. And so you see this increase, dramatic increase of the rate of reaction initially. Now let's say we change the concentration again, and we added a lot more orange particles, okay, a lot more orange reactants. So the chances of blue hitting the orange reactants now has increased, right? Because everywhere it goes is like bumping into orange particles. And so sometimes they will have enough kinetic energy, right? Most of the bumping is just resulting in nothing but sardines in a can, and nothing's happening. But occasionally what you see is that there's enough energy between the orange and the blue to overcome, kinetic energy to overcome that activation energy barrier. And because there's a lot more orange particles available to bump with the blue particles, the opposable reactants, the initial rate of reaction between in this situation is that the rate of reaction is much, much, much higher. And so how do we draw that? We're going to draw the rate of reaction being really high, and then it dramatically decreases as it reaches to the top, right? And then as soon as all the blue reactants are used up, that's it. It's not going to go any further. And so here we can compare the rate of reaction between these three different instances. So that's pretty cool, right? So generally, what happens is that when you increase the concentration, the chances of successful, let me just put this down a bit so you can look at it, the chances of successful collisions also increase, resulting in higher rate of reaction, at least at the initial stage here, okay? The rate is higher at the beginning of the reactions, like I talked about, because there are more reactants available for the reaction to occur, all right? As the amount of reactants decreases because products are being made, and assuming if the products are removed, then the products can revert back into reactants, so will the chance of successful collisions. So when reactants get used up, the chances of collisions also decreases, and the chances of successful collision decreases even further. So that's the case. But ultimately, the total number of products would depend on the limiting reagent, and this, in our case, the blue particles are our limiting reagents. So there we go. Rates of reaction, that the effects of concentration on the rates of reaction. Next time will be temperature.